Your chips aren't slow, they're hungry, and bandwidth is the food. When compute waits on memory, you pay for idle silicon, longer training time, higher bills, and jittery responses. The clearest stake is simple. Starve compute, and you lose money every second. HBM is high bandwidth memory placed right next to the processor, with very wide links that move far more data per second than conventional graphics memory. A stack is several memory chips layered vertically and connected internally, so they behave like one fast, fat source of data. GDDR, the graphics memory many accelerators still use, lives as separate chips around the board. It pushes bits by running very fast clocks across relatively narrow connections. That approach is great for cost and capacity, but those long traces and skinny buses mean the processor spends more time asking and less time doing. HBM flips that trade-off. Instead of chasing high clock speed across long paths, HBM wins by going wide and short. The memory dies are physically stacked, then placed a few millimeters from the compute die. The vertical plumbing inside each stack uses through-silicon vias, tiny copper columns drilled through the memory dies to connect layers like an elevator shaft. Those stacks sit on a silicon interposer, a thin slab that acts like a high-speed bridge between memory and the compute die. Because the bus is thousands of bits wide, each tick of the clock moves a big mouthful of data. The links don't need to scream at extreme frequency to hit high throughput, which lowers energy per bit and trims latency. Proximity matters. Short wires mean less delay and less chance the signal gets fuzzy. Now here's the cause and effect that shows up in training logs. When an attention block asks for keys and values, a narrow memory path makes the compute cores stall while data trickles in. With HBM's fat pipes, those requests complete sooner, the cores stay busy, and overall, utilization rises. More useful work per second shows up as more tokens processed per second. Let's put simple numbers to it. A typical GDDR setup offers bandwidth in the hundreds of gigabytes per second. Several HBM stacks feeding one compute die deliver in the low thousands of gigabytes per second. That gap is the difference between compute that sips and compute that gulps. In practice, that extra headroom turns into throughput. If your model's memory traffic needs about 1,000 gigabytes per second to keep the math units fed, running on a system that tops out at 500 means the cores spend large fractions of time waiting. Training slows, energy climbs, and the bill creeps up because wall clock time stretches. Tokens per second is the number you feel day to day. When you lift bandwidth bottlenecks, this figure usually tracks upward because the model's hot layers spend less time starved. Depending on the architecture and batch size, doubling memory bandwidth can yield a meaningful boost in tokens per second, even if the raw floating point capability didn't change at all. Inference tells a different but related story. Tail latency, the slowest responses in a batch or across requests, often traces back to moments when memory traffic spikes. With tight headroom, bursts collide and queues build. With HBM's wider path, those bursts drain faster, and the worst-case responses shrink. Clients don't care about average latency when the laggy one is the only one they see. Under the hood, the cache hierarchy still matters. On-die caches catch the small, hot working sets, but large models blow past those limits, and the next level is HBM or GDDR. Sequential access and prefetching help both. Yet wide HBM buses help more because the memory controller can pull bigger chunks per transaction without bouncing between chips on a board. Context length pushes memory harder than raw math. Longer prompts and wider key value caches swell the read and write volume between layers. When that volume grows faster than your compute, bandwidth, not floating point performance, sets the ceiling for tokens per second. That is why models with big contexts run smoother on systems where memory can feed them steadily. The wins aren't free. Stacking dies makes heat flow harder. Each memory layer adds a layer of thermal resistance, and the compute die radiates heat nearby, so you must budget thermal headroom carefully. If you miss, throttling wipes away the very bandwidth you paid for. Yield is another cost. A stack is only as good as its weakest die. And when many layers combine, the chance of one tiny defect rises. Manufacturers use redundancy and repair strategies, but those add complexity and time, which you see as higher cost per gigabyte. Packaging is also a gate. Silicon interposers are big and delicate. As you add more stacks or bigger compute dies, the interposer area grows, driving up cost and pushing against reticle limits in manufacturing. Larger packages also complicate power delivery and cooling, so board design gets tighter and less forgiving. Capacity per stack is limited. You can get many gigabytes in a stack, but not as many as you can scatter around a board with GDDR at similar cost. If your workload needs very large memory capacity more than it needs extreme bandwidth, GDDR can still be the right answer. Cost per gigabyte is higher with HBM because the process adds 3D stacking, TSV drilling, and specialized assembly. If your workload is compute-bound or sits comfortably inside on-die cache for most hot paths, that premium may not buy you much. GDDR's strengths are real. It scales capacity well, benefits from mature supply chains, and keeps package complexity modest. For workloads with moderate bandwidth needs and large model checkpoints that must sit in memory, GDDR offers a good balance, especially when you can shard across multiple devices and hide some latency with batching. But when your traces show the math units waiting on data, HBM shifts the balance. Reducing stalls increases effective compute, which means you get more work from the same silicon. The power draw per token also improves because memory energy per bit is lower and idle cycles drop. For a quick rule of thumb, match the memory system to the traffic pattern. Streaming regular access patterns thrive on wide HBM channels that keep the pipeline full. Highly random pointer-chasing patterns still benefit from low latency, but caching and software layout may help more than raw bandwidth in those cases. Looking ahead, capacity per HBM stack is rising as memory dies pack more bits into the same footprint. That means you'll see larger models fed by the same number of stacks, or the same models with fewer stacks and simpler packages. At the same time, power and thermals will remain the guardrails. Tens of watts per stack add up quickly next to a hot compute die. Packaging limits will shape the near term. Expect more advanced interposers and bridge technologies to squeeze extra stacks into a sane footprint, but not without trade-offs in cost and yield. There is also a practical ceiling on how many stacks you can cluster around one compute die before routing, power, and cooling get in the way. On the system side, standards for memory coherency and chiplet interconnects are maturing, which will let designers mix and match compute tiles and memory stacks more flexibly. The promise is simple. Put bandwidth where the algorithm needs it, not just where the package allows it. Energy per bit will be a headline constraint. Even efficient wide links consume power, and data centers are bumping into power and cooling caps. Feeding compute efficiently, moving fewer bytes through smarter layouts and compression, will compete with feeding it faster. Here's the principal takeaway. When your performance charts show high stall time and tokens per second rising mainly with memory tweaks, bandwidth beats raw floating point horsepower. When your model is compute-bound with caches doing their job, capacity and cost per gigabyte matter more than exotic packaging. To make it concrete, remember this checklist. First, profile memory traffic and stalls before buying more flops. Second, choose HBM when bandwidth in the low thousands of gigabytes per second will directly raise utilization. Third, choose GDDR when you need lots of affordable capacity and your bandwidth demand sits in the hundreds. Subscribe for more Future Forge.